The next question was about resistivity and so forth, and this is actually a fairly easy question, but you need to understand the concept of resistivity and the fairly simple relationships that govern it. So, first of all, just to give you a little context, you know that the resistance of a piece of nichrome, you experience this directly in lab, was greater if you had a greater length. Now, we didn't actually get to verify that it's also less if you have a greater cross-sectional area, but that is the case. So that the resistance is length divided by cross-sectional area times resistivity. And all these are nice and linear or reciprocal linear. And we're going to see why. Okay, so let's say we got a cylinder, and we usually on the test, at this point at least, describe a wire as a uniform cylinder with a certain cross-sectional area and a certain length. Okay, so we've got a uniform cylinder of a certain cross-sectional area between a point A and a point B, and the distance between those points is L. Now we have some voltage from A to B, so we have a voltage change from A to B. Okay, well, the electric field then in here, this is a uniform cylinder, and we're assuming a uniform material. It's the same material throughout, and that means that the, again, a symmetry argument will show it, that the electric field from here to here is going to be uniform. Okay, so we have uniform electric field, VAB over L. Now there's some slight effects near the edges, and I'm not going to mention those. That it doesn't make a hill of beans difference in our analysis. It follows then that the force on a charge Q is QE. Okay, so if Q is, for example, an electron, and the electrons, and this is a metal, then the free electrons in the metal are all going to be subject to forces F equals QE. Now, for any reasonable voltage and reasonable length, this force is going to, on an electron, is going to be so great that in a nanosecond to several nanoseconds, the electron is going to theoretically get up to the speed of light. Now, because of relativity, it's not going to get up to the speed of light, and it's not probably going to get there anyway, because you have all these electrons in here bouncing around thermally. Electrons have very small mass, which gives them a very large thermal velocity. Okay, so they're going to bounce off of each other before they get up anywhere near the speed of light. The result of that is that in a typical metal with reasonable voltages, and any voltage that doesn't melt the metal, the electrons are going to drift fairly slowly, maybe a few millimeters per second, maybe up to a few centimeters per second. Anything more than that, you're probably going to melt your material. So you got this whole cloud, many electrons moving slowly through this conductor. Okay, that gives you a large current. Even though they're moving slowly, there's so many of them that a lot of coulombs are going to pass a given point in a second. So you're going to get a large number of amps. Now, if you get a smaller voltage, maybe you'll get a fraction of an amp, or a long conductor where you have a small electric field that doesn't accelerate the electrons much, maybe you don't get as much current. Okay, so this leads to the fact that your current density is going to be proportional to your electric field, okay? Because it's the force which results from the field that accelerates the electrons, so the drift velocity of the electrons is going to be proportional to the E, so the current density is going to be proportional to E. Now, what do I mean by current density? I mean the amount of current per cross-sectional area. Very simple idea. Okay, so the amount of current per square meter, although you're usually looking at dimensions less than a square meter, it could be the amount of current per square millimeter or per square micron, whatever you want. You have a certain current density that's proportional to the electric field. Now, that proportionality depends on many things. How much the material itself interferes with the flow of free electrons. Also, how many, what density of free electrons you have within the material. That's going to vary from one material to another. Okay? Now, well, since the current density is I over cross-sectional area, then I over cross-sectional area is proportional to the electric field. Now the electric field, which is voltage divided by L for given voltage, is proportional to the reciprocal of the length. The distance between A and B, the length of your cylinder. So that your current is proportional to the cross-sectional area divided by the length of the cylinder. And you could also say, you could throw V in there if you want, but since the resistance is voltage divided by current, and then the voltage is going to divide out, and you're going to end up with resistance being proportional to the length over the cross-sectional area. And the proportionality constant we're going to call rho the resistivity. So you got R equals resistivity times L over cross-sectional area. And that, again, makes perfect sense of what you saw with the nichrome, what you experienced in the lab. Okay? And this rho is what we call resistivity. It's the proportionality constant that depends on the density of electrons in here and how much the material interferes with the drift of the electrons. And that's your proportionality constant, the resistivity, that depends on the material. Now, the problem that you asked me about, I gave you a list of resistivities. So it's very easy then if you have a situation to look up the resistivity, or if we have a situation where you're given the resistance, length, and cross-sectional area, it's very easy to calculate the resistivity. You only have 4 quantities here, and as soon as you understand this proportionality, you have a formula that you can use to solve for any one of these if you know the other 3. And of course, I ask you questions that ask you to do that with various combinations of given information. Okay, in this case, we want the resistance to equal 100 ohms if the cross-sectional area is 1 square centimeter. Now, the problem gave you a set of resistances, and it said silicon is kind of in the middle. It's a semiconductor. Its resistivity is around 1 ohm centimeter. So we're asked to find, in this case, the length of a cylinder of silicon with a resistivity of 1 ohm meter, such that the cross-sectional area is 1 square centimeter. So we have a 1 square centimeter area. We want to know how long silicon cylinder would need to be in order to have 100 ohms of resistance. Okay? So, well, the value I gave for silicon was 1 ohm meter, and that's a fairly typical value. It can vary. It could be 1/10 of that. It can be 100 times that, even more, depending what kind of impurities are present in the silicon. Okay, and that's what makes silicon a really kind of a good material to use in semiconductor devices. Now, we haven't talked about those, and we're not going to in this course, but that underlies all of modern electronics, transistors, computers, everything. Okay, so with that little digression, it's a simple question. R is 100 ohms, cross-sectional area is a square centimeter, rho is 1 ohm meter, and we want to find the length. Okay, we know cross-sectional area, we know rho, we know R. Well, let's solve this for L. And I have A here, but I don't have a CS on it, so let's make sure we got CS so we have a consistent reference. And so solving this for L, we get L equals, well, multiply by ACS divide by rho. And we get this, which gives us this. And when we multiply this out, we end up with 100 square centimeters over meters, and times ohms. I'm sorry, no. The ohms divide out, ohms divide ohms. We end up with 100. Okay, and we have square centimeters over meters. Square centimeter over meter is a square centimeter over 100 centimeters, which is, well, no surprise, 1 centimeter. So that this fairly typical silicon object, it's not a disc because it's too thick, it's a cylinder, but it has an area of 1 square centimeter and a length of 1 centimeter, okay? And that's kind of a point of reference for understanding something about resistivity, and then we go on to extend that just a little bit in a pretty simple way.